All right. Well, hello, welcome everyone. This is a joint webinar between Morningstar Corporation and Rolls-Surrett Battery. Today we're going to be talking about maintaining healthy batteries in off-grid systems. I am Jake Sherry, an applications engineer with Morningstar, and joining me today is Steve Higgins, technical services manager for Rolls Battery. And we'll go ahead on to the next slide here to take a look at the agenda for today. So we'll just give you a little bit of corporate background for both companies, Morningstar and Rolls. Talk about specifics of choosing the right type of battery in designing an off-grid system. Go through specific sizing calculations. Talk about the recommended charge settings for specific configurations of system design. Of course, choosing and installing the right controller. I'll go ahead and talk about that. The programming of the charge settings and some remote monitoring capabilities that may be available to you with charge controllers. And we'll go back into a deep dive into the battery maintenance, some best practices, sum things up, and then end things with a Q&A. So without further hesitation, we'll go ahead and just give you a little bit of rundown on Morningstar. Morningstar is a U.S. company. We conduct business through authorized distributors and dealers all over the world. Been around since 1993, and we've been a leading supplier of solar charge controllers and inverters. We've had the same ownership, management, distribution partners as well since the very beginning. Take a lot of great pride in our product quality, reliability, and innovation. And since our inception, over 3 million Morningstar products have been supplied worldwide. Each year, you'll typically see us at various trade shows, big solar events, Intersolar Europe, many other shows and conferences throughout Europe, Africa, Asia, Australia, and as well as North and South America. I'll go ahead and pass it back to Steve, who will give you a little bit of a rundown on Surrett.
Yeah, this is Steve Higgins. Again, I'm the technical services manager for Rolls. We were established back in 1939. We've been making batteries generally for the last 80 years. Primarily, we make deep cycle lead-based batteries for renewable marine, motive power, or railroad applications. Couple things about Rolls. We were initially made in the USA, out of the Boston area. The Rolls brand initially is in the USA, Surrett basically everywhere else. Rolls USA went out of business in the 2000s, and we purchased the name back. So, flooded cells, deep cycle lead acid batteries, wide product ranges from 2 volt all the way up to 12 volt, from 80 amp hours all the way up to 160 amp hours. Sealed maintenance-free batteries, both AGM and gel products. 612 2 volt models, 80 amp hours all the way up to 3300 amp hours, and 2 volt gels from 215 amp hours all the way to 3200 amp hours. Renewable energy. The product line for renewable energy for our product varies. Generally, it's about 55. It can swing from 40 to 55% of our business, depending on from year to year to year, depending on what rail and what marine's doing. We currently have inventory in 10 countries and probably 5 continents now. And we've probably got closer to this slide was written a few years ago. We've probably got close to 70 to 75,000 of off-grid installations all over the world, installed around the world. We are ISO 9001 2008. We are also we're going through some of the newer ISO recommendations, so that should be updated soon. We are also IEC tested, both our Series 4000 and our Series 5000 batteries, 4000, 4500, and 5000 batteries. We are IEC tested. So, and we've passed those certifications. I think I'm gonna go ahead and start. The first thing you need to understand about batteries is the mistakes that most people make, and that's classified under choosing the right type of battery. The number one mistake that most people make when they are sizing or designing these solar systems is they oversize the battery bank. The idea of going big or go home with solar just doesn't work. One of the problems that we have today, that battery companies have today, and a lot of solar installers have today, is 20 years ago, the person who moved off grid understood conserving electricity, understood conservatism and taking care of the earth and all that. Today, what's happening is that you have people who are living on grid who want to move off grid because they're frustrated with the cost of grid, or they are just trying to get away from the hustle and bustle. And so what they do is they try to run their entire house on battery banks. So the batteries get so big, and then they don't have enough solar or enough renewable to take care of it. The second problem that we see a lot with these systems is too many parallel strings. I spoke to a gentleman yesterday with 6 parallel strings of batteries, and he was amazed that we could do the same capacity battery bank with 2-volt cells, and it would be a lot cheaper. So try to avoid multiple parallel strings. The more parallel strings you have to charge, the more problems that you can have. Next, taillight installers are a problem. When you install a battery-based system, regardless if it's battery-based grid tie, battery-based backup, or battery-based off-grid, you are now married to that client, which means you need to make sure that you take care of that client, because every time you don't, what's going to happen is that client's going to badmouth your company. And so you want to be careful that you take care of that client and you don't abandon them. So you want to make sure with a solar system, you need to follow up with that client to make sure that they're charging the batteries or maintaining the batteries properly. Because if they're not charging them properly, and if they're not maintaining the batteries properly, of course, regardless of the battery manufacturer, the warranties will be void. Make sure you understand the product that you sell. What that means is that if you're installing a Morningstar controller, make sure you know how it works. Make sure you know how to program that controller. And the reason for that is that they're all different. They all have different little things, little idiocies that's difficult, that can be difficult to understand. Same thing goes for batteries. If you're going to install Rolls batteries or Trojan batteries or any type of battery, you need to understand how that battery works and what that battery is required to operate. You need to understand that charging voltages between all the different battery manufacturers in the solar industry is different. You need to understand that specific gravity measurements are slightly different between each battery manufacturer. Not understanding the pluses and minuses of different battery chemistries. Most flooded lead acid batteries are what's called a lead antimony battery. A lead antimony battery wants to cycle. Most valve regulated lead acid batteries are a lead calcium battery, and lead calcium batteries want to float. And so if you put a lead antimony battery in a backup application and you never cycle it, that battery can have problems down the road with capacity. You're going to lose capacity. The battery will test okay, but when you put a load on it, you'll lose capacity. Next one, getting into the DESA cycling trap, and this is pretty common. And this is tied back to the insufficient solar and other renewable resources installed. And that's why I skipped it. Make sure you have enough renewable. Make sure you have enough charging sources to get your battery bank charged within a reasonable amount of time. For Rolls product, on an off-grid solar system where the battery bank's being cycled daily, we want to see a full 1265 to 1275 specific gravity at least once every 7 to 10 days. If you go longer, then what will happen is that'll start deficit cycling, and if you don't have enough renewable installed, you'll never get that battery bank to a fully 100% charged. Last but not least, not getting the absorption times correct. This is one of those settings that people have a hard time getting programmed. We have a formula for setting it. In the last 2 weeks, I've probably been to 15 sites from Puerto Rico to Northern Ontario. In every single one of the sites, the absorption times were defaulted at 1 or 2 hours, regardless of the manufacturer's product. So make sure you get that product installed correctly. Batteries, lead acid batteries, and for that matter, lithium batteries are all temperature sensitive. What makes the battery work is a chemical reaction. That chemical reaction is based at 25 degrees Celsius or 77 degrees Fahrenheit. So if your temperature is 25 degrees Celsius, that's where you're going to get your the most power, the most efficiency, the longest lifetime out of your batteries. If, say, your batteries are in Puerto Rico and they're installed in an outside lean-to along a building, and the average temperature is between 28 and 32 degrees Celsius, those lead acid batteries, regardless of the manufacturer, you're going to lose 25% of your cycle life. If that same battery bank's installed in Northern Ontario, where you might see negative 20 degrees C temperatures outside constantly for 4 to 6 months of the year, if those batteries are measuring 15 degrees Celsius, you're going to lose 15% of your capacity. And that the lower those battery temperatures go, the higher you need to size the battery bank. So high temperatures damage cycle life. Low temperatures take away capacity, but once the temperatures return back to 25 C or 77 degrees Fahrenheit, you will return your capacity. All right. To properly size a system, and I bolded and underline it, you must know how much energy is being consumed. If you're making a guess or an approximation, it's going to be a guess or an approximation, and there's a good chance that you're going to be wrong, or in worst case scenario, you're not going to have anything back on the client. What often happens to these systems is you go and you install and you design a system, you drive away, 6 months, 12 months, 18 months later, the client's calling you and telling you that the system doesn't work as well as it did when you first installed it. You go out there and you find he's put a 12-person jacuzzi tub in the backyard. So you want to be careful with that. You need to figure out how much energy you need to produce, and you must power the loads and charge the batteries. If you size your array to only power the loads, and your customer is always running those loads, they're never going to have excess power left over from the free solar to charge those batteries, and they're going to have to run the generator. And as we all saw 4 or 5, 6 years ago, when petrol and gasoline and diesel were all $3.50 to $5 a gallon, and some places internationally, up in Canada, they're still paying $1.40 a liter for gasoline. Fuel is expensive. Fossil fuels are expensive. They're only going to get more and more expensive as we run into more and more problems. So you want to make sure that's taken care of. So here's a generic system sizing that I did for my house back in the early 2000s. I was living in the Mojave Desert at the time. I've got some lighting at the time. LED lights weren't common, so the lighting's a little high, and then heating. Heating's a little high because it does get cold in the desert in the wintertime. So a couple things, but this is ballpark average. So 15.75 kilowatt hours per day. You need to do this. If you don't do this, you don't know what these numbers are. If I was doing a system design, you show this to the customer, you have them sign it saying, hey, this is what your loads are. If your loads go up, you're going to need a bigger system. So something to keep in mind. So real quick, battery sizing calculations, and I'm only showing the watt hour calculations because that's the way I like to do it now. Used to do amps, but when you start talking amps to end users, they tend to glaze over and they don't really understand. Watts tends to be a little easier to handle for the customer. So if you take that 15,750 watt hours, you add 15% losses. So you add your 15% losses. So you multiply it by 1.15. That gives you 18 kilowatt hours, basically 18,112 watt hours. Divide that by 0.5 for 50% depth to discharge. So we're going to assume we're going to discharge these down to 50% before we do a full recharge. So that gives us 36.2 kilowatt hours of energy. So for 1 day of autonomy, you'd need that 36 kilowatt hours of storage. So you take that 36 kilowatt hours and you divide that by your nominal battery bank voltage, which gives you 754 amp hours capacity. Okay. A couple more things that you need to worry about. Of course, temperatures, where the battery is going to be installed, your solar productions, depending on the type of year. But this is just a basic system sizing, basic battery system sizing. The nice thing about this is that when you tell your client, when your client asks you, okay, I need a 36 kilowatt hour battery bank, okay, you tell the client you have 18 kilowatt hours of usable storage, which means you can run 1,000 watt loads for 18 hours. You can run 500 watt loads for 36 hours. Or you can run about, with Pukerts, you're going to run about a 12 kilowatt to 14 kilowatt hour load for 1 hour, and your batteries are dead. And so you can easily tell the client you can run 1,000 watts for 18 hours, and that you're going to be relatively safe for that. Okay. So summary. Oh, looks like my marks didn't clear. There we go. So summary: off-grid home, 1 day of autonomy. You're going to need 36 kilowatt hours or 754 amp hours of storage, using 15% losses and assuming a 50% depth of discharge. For 2 days, a lot of people will just say double it. Well, not really. If you add another 18 kilowatt hours and make sure you have enough array to keep those batteries in that 95 percentile charge rate, even with the loads, you can get away with not having to add more batteries. As a battery company, I'm telling you this because I'd rather you put more array on my batteries, keep my batteries at a higher state of charge. They're going to last longer the longer they stay at that higher state of charge. All right, so battery sizing, we're still in the battery sizing calculations. When you start talking adding PV array, you start say for this example, we're going to put in a 750 amp hour battery bank, a 750 amp hour battery bank. You should have one source that's capable of at least 10 to 20% of the C20 amp hour capacity, which means when I'm charging this battery, I want to have at least one source of 75 to 100 amps of charge current to charge those batteries properly. Okay, preferably renewable sources, because once you buy a solar panel, once you buy a hydro, other than the maintenance, or the wind generator, other than the maintenance that you have to do, it's free energy. You don't have to pay any more for it. Okay, especially solar. You put in solar, you clean it off, once a quarter, once every 2-3 months, depending on where you live. You're good to go. So on average, at 48 volts on a 750 amp hour battery bank, you're going to need roughly a 4 to 6 kilowatt array, depending on where you're at a minimum, to keep that battery bank fully charged, regardless if it's anybody's battery. This is all batteries. You're going to need that because a lot of people overstate what the arrays will do. I see it all the time: 700, 800 amp hour battery bank with a kilowatt of solar, and the customer is struggling to keep the batteries charged. The maximum solar array, especially on a flooded battery bank, would be an 8 to 9 kilowatt of solar. There is a maximum, a minimum of 10%, a maximum of 20%. If you put too much current into especially a flooded lead acid battery, or even a valve regulated battery, if you put too much current into it too quickly, it'll cause positive post expansion and cause the battery to fail early. All right, so recommended charging voltages, batteries, lower charging voltages, they're the bonus. Batteries remain cooler. That's a huge thing. So the nice thing about lower charging voltages, the batteries remain cooler. That maximizes overall service life, and you're going to use a lot less water while you're doing it. The problem is that sulfation is going to occur. If sulfation is occurring, that means that's going to limit your overall service life, especially if your client's not keeping track of it. If they're not monitoring their specific gravities, they're going to run into problems. And it also means slower charge times, which means you're going to consume more fuel, or you're going to have to install more solar to keep those batteries at a full state of charge. Higher charging voltages. As soon as it gets there we go. Higher charging voltages depend on a couple things. You get faster charge times, you get more consistent capacity readings, you get less sulfation problems. Okay, you're going to get more gassing, which means you're going to have more hydrogen accumulation, more frequent wiring to be required, and the higher temperatures can cause active material shedding if the temperatures aren't controlled. It's like balancing your life. Okay, if you eat too much and you don't exercise enough, you're going to get heavy. If you run too much and you don't eat enough, you're gonna cause problems with your muscles. You're gonna start causing damage to your body. It's all about a balance, especially when you're dealing with battery-based systems. It's all about balancing and educating that client to make sure they stay balanced. When they start using too many loads, when they start doing things that cause problems, they're gonna give you issues. How batteries charge in general. We've all heard this, how batteries charge in general. This is a standard three-stage charge algorithm. You have the bulk mode, you have the absorption mode, and you have the float mode. All the other modes, refloat, rebulk, silent, cell, all those other modes, generally battery companies don't really care about them. Okay, those are a lot of times that can be marketing issues. So for Rolls batteries, bulk mode typically is 2.45 to 2.5 volts per cell. So if it's a 24 volt system, you're talking 29.2 to 30 volts. And so when you're charging in bulk mode, the batteries, say we start our charge at about 2.1, 2.0 volts per cell. When we get to this point, you are at about 80%. And this is going to look pretty ugly, so I apologize. I did pretty good there. So you're only at about 80% charge. The issue is with most controllers, most inverters out there, is that 80% is often represented as a blinking light or solid green light. So a lot of clients, when they see that, oh, my battery voltage is up to 58.8 or 59.2 or 29.6, or if it's above that bulk voltage, oh, my batteries are charged, and they shut off their chargers. Okay, the most important stage in charging a battery is this absorption stage. If you do not complete this full absorption stage, at least that once a week, and at the end of that absorption stage, you are not getting to that 1265 to 1275 specific gravity for Rolls batteries, you are undercharging your batteries and you are causing damage to your batteries. Okay, and so we have a formula for determining the absorption time, and this is the time equals 0.42 multiplied by C20 divided by I. And I'm going to explain that here in just this very next slide. There we go. So how to calculate absorption time. I'm sorry, everything populated already. But how to calculate absorption time. So 0.42 multiplied by the C20 divided by nominal current. 0.42 is the assumption. It's the assumption that you will lose 50% to 60% of your overall charging current while in absorb. Okay? That is the assumption that you're going to lose, because what happens is as that battery becomes full, the battery can't accept any more current. So what's happening is that the charger sees that high current, that full, the battery starts to reject current, and so it starts to back off the charge rate. It's not the charge controller's fault that it does that. It's not the inverter's fault that it does that. It's the battery. It's just like pouring a pitcher. If you take a pitcher and you're pouring into a glass, when you get to that 70, 80, 90%, you start to back off the pour so you don't overfill. The batteries do that. That's part of the chemistry that works within the battery. This is not depth of discharge. Okay, that 0.42 is not depth of discharge. So be cautious with that. A lot of people think that that's depth of discharge, so they'll change that number. We already know we're 80% depth of discharge. We're already assumed that we're 80% depth of discharge when we hit that bulk stage on a healthy battery. So that is not depth of discharge. The C20 is just the C rate, the 20-hour rate of the battery. So if you're putting in a 500 amp hour battery bank, like the example over here, that's just the C20 rate. So that's what that is. The nominal current. Nominal current is the nominal charging current while in bulk. And what that means is that's how much current that the inverter or the charge controller is putting into the batteries while you're in bulk mode. So, and I've got some examples on the other side that I'm going to walk through here real quick. It's a good idea, you know, if my solar array is a 1,000-watt array and I'm charging it at 24 volts, I know that I'm going to see ballpark between 20 and 22 amps of peak current, but my nominal current, I'm going to derate about 15 to 20%, just because I know you're not always getting that 1,000 watts per square meter of sun on your panels. There's always stuff going on with the panels, heating, temperature durations. There's a lot of things that go on with the panels that can cause that. The other thing that's a good thing to do, especially if you're an installer, go out there with your meter and take an actual reading at 11, 12, 1 o'clock in the afternoon and see what the actual current going into the batteries is, in the bulk stage. That's a good idea because that way you can be a little more accurate with your calculation. Just to give you an example, one of the sites I was at last week, the inverter was displaying it was charging at 105 amps. When we put the current meter on it, it displayed 87 amps. So either the inverter was measuring the incorrect current or the meter was measuring the incorrect current. And so we put a couple separate meters on there, and they agree with the meter. And so what a lot of inverters will do is they will just make a calculation based on the volts and the watts and try to get current out of the Ohm's law and not take into account any of the losses. So be cautious with that. So for example, we have a 500 amp hour battery bank at 48 volts. We have a 2000 watt array. A 2000 watt array peak is going to do roughly around 30 to 35 amps of current. Okay. So on that specific one, let me pop into the pin again. So that specific one, our absorption time is going to be about 6 hours on that battery bank. Okay. A 1000 watt array at 21 amps of peak current, roughly 15 to 18 amps. On this specific array, our absorption time is going to be about 11 hours. And a 3000 watt array at 62 amps peak is going to do roughly about 3.8 hours for absorption time. So same battery bank, 3 different arrays, 3 totally different absorption times. Be cautious with that because a lot of times people get this absorption time too short, and having it too short is just going to undercharge your batteries and cause problems. So I think this is last but not least, but we'll just, so it's important to make sure that you have a battery temp sensor installed. When we start talking about charging batteries, if you do not have a battery temp sensor installed, I don't care if you're in Hawaii, I don't care if you're in Zimbabwe, or if you're in the Mojave Desert. You should always have a battery temperature installed on your batteries. And the reason for that is that when you're charging the batteries or you're using the batteries, the temperature of the batteries is going to be higher than ambient. And especially if you're charging the batteries and your temperature goes much higher than what your ambient temperature is, it'll typically get between 8 and 15 degrees Fahrenheit higher than what the ambient temperature is. What will happen is now that results in an overcharge for the batteries, and that can cause a problem. So the purpose of the battery temp sensors is to adjust the charging voltage depending on the actual temperature of the batteries. Battery manufacturers will void the warranties on the batteries if you're not properly using temp sensors. Here's a couple of examples. Sorry, the picture's a little bit small, but if you notice where the battery temp sensors are installed on these, on this one, the battery temp sensor is installed on the side of the wall of the cabinet, of the container. On this one, the battery temp sensor is installed on the top of the battery. Battery companies don't want the temp sensors there. Battery companies want the temp sensor on the side of the battery, about halfway down you want them below the level of the plates, because otherwise the temp sensor is having a hard time doing its job. So with the Morningstar BTS, it typically has a bolt onto the terminal. As a battery manufacturer, we prefer that you just take that terminal, and I've tested this on a couple recent installations to make sure it worked. Just take it, use electrical tape or even duct tape. Hold the temp sensor on the side of the battery and just duct tape it to the side. For flooded lead acid batteries, your temp sensor ratings is plus or minus 5 millivolts per degree C multiplied by the cells. So at 48 volts, you're adjusting 0.12 volts per degree Celsius. On a AGM battery bank, it's 4 millivolts, so you're going 0.096, and on a gel, that's 0.072. And so where this is important is if we look at the charging settings. So this is our charging chart for regularly cycling or partial state of charge recovery. And so what you do is if you're using a battery temp sensor, you're going to program your charge controller. So if you have a 24 volt system, you're going to program your charge controller to charge at 30 volts. That's where you're going to set your bulk and absorption voltage. Okay? You're going to set your float voltage at 27 volts, and you're going to set your equalization between 31.2 to 31.8. Okay? And so by doing that, what that does is you're allowing the temp sensor to make adjustments based on what the actual temperature of the battery is. Just to give you an example, of that. Just to give you an example of that, now that I erased all that stuff. So if you're using a battery temp sensor and your battery temperature is 30 degrees Celsius or 86 Fahrenheit, and you left the battery charge settings at default, your bulk absorption voltage should be 30 volts. Your charger should be charging at 29.7. Okay, but if you left it at default, what'll happen is, but you set it for 29.7 volts, your charger will charge at 29.4 when it's supposed to be high, when it's supposed to be a little lower than that. So what will happen is that you'll actually be, in effect, what's called double temperature compensation. So what you're doing is you are undercharging your batteries just based on that lower charging voltage. So be careful with that. Make sure you follow the battery recommendations. Make sure you understand that. Here are some settings that we have for our flooded batteries, and then we have two different charts now. We have a frequent cycling, so if it's a full-time backup, a full-time off-grid system, then we want to be a little more aggressive with our settings to get the higher capacities. If you've got an infrequent cycling system or a backup type system where the customer is not using it very often. Perfect example for this is the guy that's got the cabin in Montana, and he's out there for 2 months of the year, and he's out there for 2, 3, or 4 weeks, and he's gone for 4 or 5 months, and he's out there for 2, 3, 4 weeks, and he's gone for 4 or 5 months. So what you do is you set that when he's there, you have him set his charging voltages at the more aggressive charging voltages. When he leaves, then what you do is you have him set his charging voltages at a little less aggressive number, so they're not gassing as much. So you're not beating them up as much and hammering on the batteries as much. We move on, and so these are just some of the charging settings for some of our product AGMSs, and I'm gonna even talk a little about them, but AGMSs, AGMRs, and gels. And so if I have for example, a ProStar charge controller, I've got 8 S550s connected in series parallel, so I have an 856 amp hour battery bank, and my client has a 2800 watt solar array on 2 ProStar MPPT 40s. Then what I'm going to do is I'm going to set my bulk and absorption voltage with temperature compensation at 30 volts, because I'm going to be doing a maximum of 80 amps, but I've got two PV arrays that are going to clip earlier in the day. I'm going to set my absorption current at 75, so my absorption time is going to be 4.79 hours. So ballpark, you may need to adjust that depending on seasons. The ballpark, that's about where you're going to be for your absorption time settings. We move on to one more system example. Oops, sorry, that went too far. If I go with a little bit larger array on 3 charge controllers, now I have 3 charge controllers. I'm going to see a peak of that 120 amps of current, but what will happen now, I have a peak of 120 amps of current because I got 3 MPPT 40s. Now I'm going to derate that about 20%. And so now my absorption time goes to about 3.5, 3.6 hours. And so you can see the relationship between having a little bit more charge source versus having a little bit less charge source, and making sure that absorption time gets set up properly. So now what I'm going to do is I'm going to pass it back over to Jake. I've talked too much, and there you go.
That was very good, Steve. Thank you very much. I will go through a little bit on the controller side and then pass it back over to you when I'm finished. Let's see, everybody see my screen okay? Looks like it's showing. Should be good there. Okay, 1 second. All right, so the diagram that you see here is a typical off-grid DC system with a DC load. So, Steve talked about batteries really being a core component of an off-grid system, definitely the most expensive component. And then the other central component to this system operation is the charge controller. So just to talk about it, Steve, at the end of his portion there, was going into some sizing examples using our ProStar MPPT controller. And so I'll just segue from there and talk about some of the features that are unique to this controller and make it very easy for programming these different battery specifications. So we'll go through the process there using the built-in meter display. So just to reiterate what's going on here, and let me just take out my pointer. So we have sunlight striking the modules. That's converting it into DC electrical power, feeding the controller. The controller is then going to regulate that power in terms of amperage and voltage. First and foremost, what's required to drive the load. If that's in operation, anything excess is going to go to the battery and regulate based on those stages of charging Steve talked about. And then during the evening, of course, when there is no sunlight, the battery power is what's used to drive the load if that's still in operation during those times. So just to point out some other things from this diagram that are important to note, you do see here that the battery is grounded at the negative terminal there. That's what that symbol means. So just to emphasize why that's important for Morningstar controllers, all of our PWM and MPPT controllers do have a common negative ground. So this allows you to establish a common ground for the whole system, grounding everything on the negative side through the battery. So that includes the solar array, the battery, and the load, all sharing that common negative. This, of course, meets National Electric Code requirements in the States. If you do need an equipment ground as well for any metal parts on the controller enclosure, some of our controllers do include an actual equipment ground terminal lug inside the casing. And so you can use that as your wiring point. Otherwise, for the controllers that don't have that terminal lug, you can just connect an equipment ground directly to the metal parts of the enclosure. So again, the controller you see here in this diagram, this is our ProStar MPPT. It's actually one of our newest MPPT controllers, and as such, it really does offer many of the most modern, useful communication options, very sophisticated self-diagnostics information as well. So we'll just take a look at some of these capabilities on the next slide, just to give you an idea. So in particular, again, a very intelligent controller here. What you see on this slide are, some of the fault indications that you can receive through the internal self-diagnostics that are always aware as soon as you plug it into battery power. It's able to diagnose, anything that may occur during various steps of the installation process. And of course, during normal operation, if there's a load short circuit, if there's a load overcurrent, solar short circuit, battery reverse polarity, or solar high voltage disconnect, you'll be alerted through various means, either through the LED, the status and battery LEDs there, or on the metered versions, you'll see it written out in descriptions on that meter display. So here, for instance, just to highlight the first one, the load short circuit fault indication. If there is one that has occurred, the error status LED is going to flash there, and then the battery status LEDs are going to flash in a particular sequence. You have the red and the green together, and then yellow. So if you did see that happening, you didn't know what it meant, you could go to the fault section of the operation manual, and you'll see that listed as one of the possible faults. Some other controllers don't give you that much information to pinpoint the exact nature of the fault. They'll really just have a single blinking error that's triggered anytime there is a fault, and then you have to dive in a little bit more deeply to identify the specific error. And of course, the other indications that you'll receive, the remote temperature sensor fault is another one. high voltage disconnects, high heat sink temperature. You'll see this in a second. Any faults associated with dip switch and custom settings changes. You'll see that as we're going to use the charge controller's meter interface to program some of the settings that Steve talked about in his sizing example. So we'll go ahead and do that now. So what you see here, just important to mention before we get started, is there's a selection of 8 dip switches on many of our controllers, and as is the case on the ProStar MPPT. If you're going to be doing custom settings, which again is highly recommended to ensure that you're giving the battery the proper treatment, as I'm sure Steve will agree, not using the appropriate settings for your battery can significantly alter the battery's lifespan. You're talking a matter of years. So again, it's really important to use those proper custom settings. And it's very easy to do, especially with this controller using the integrated meter display option. Makes it much easier. You don't have to connect to a laptop or do anything fancy in that regard. So to enable the custom settings adjustments, the first thing you want to do is put dip switches 4, 5, and 6 into the up position so that they are on, and that will select a custom charge profile, which will unlock the meter menus so that you can custom program the settings that you'll see in the following demonstration. So let me just bring up my camera here. Okay, hopefully be able to see that in just a second. It just takes a little bit to load up. Hopefully everybody can see that. Okay, so here what we're going to do is go ahead through maybe like 5 different settings adjustments that might be useful to the end user here. Hey Steve, can you chime in and see if you can see this on your screen, or has it not loaded yet?
Yeah, I can see the 0 amps, 12.15 volts LVD.
Okay, good. All right, so it looks like it is loading. Everybody should be able to see it. So now we'll go ahead through the settings adjustments. Thanks, Steve. So one of the most common alterations the user may want to make is setting the absorption voltage. And so we can go ahead and do that simply from the meter button navigation that I'll demonstrate. So to get out of the rotating home screen, you just press the down arrow and you're into the main menu. And so then what you want to do for most of the most basic custom settings, you can just go down to the custom menu option. You'll press the right arrow button to select, to enter the custom menu, and then you'll be able to choose from advanced, charging, load control, and so forth. You want to go ahead and enter the charge settings. And you'll see absorption voltage is the first one that pops up there, so we'll go ahead and select that. Now here on this screen, you can see a couple things. Current is what the controller is currently set for, so that reads the 14.7 that you see on the screen there. The factory default is 14 volts. Now again, this is for the 24 volt sizing example that Steve used in his system. So just important to keep in mind that the values that you input here into the controller are going to be based on 12 volt nominal values, even though we've also selected with our dip switches, dip switch 2 and 3 are configured to manually detect the 24 volt input. So on the battery side, the controller will multiply whatever setting is programmed in here by 2 for the 24 volt setting. So for instance, I think Steve mentioned 30 volts is roughly what we would want our bulk absorption set point voltage to be. for a 24-volt battery. So again, the 12-volt equivalent here would be 15 volts. So we'll just go ahead and hold down the right arrow until the display starts blinking. And now that allows us to edit the voltage there. Once we have it at 15, we can go ahead and save that. Set absorption voltage, yes. Now the absorption voltage has been saved, and it tells us to reboot the control. So you see here that the status, the charging status LED, as well as the rotating sequence of battery state of charge LEDs are rotating. So that indicates a fault indication that you've changed something. And now, in order for the new settings to be set into permanent memory, you do have to power cycle the controller, which I'll show you how to do very easily from the meter display once we're finished adjusting these other values. But while we're at it, we'll go ahead and just make these other custom settings adjustments. One other one I think is important to highlight is the absorption timer that Steve mentioned. So taking, for instance, his second sizing example with the 3 ProStar MPPT 40s, I believe he came down to absorption time of 3.59 hours, which, again, if we convert that into minutes, that's going to be roughly 215 minutes thereabouts. So again, we'll do the same thing, hold it down until the display starts to blink, and then we can go ahead and adjust the value accordingly. Changes pretty quickly, so we can just go up to 215. We have it there. We'll click save. Again, it will ask us to confirm yes, and it'll give us that reboot message once again. Now it's temporarily storing all this information, so we'll only have to reboot the controller once when we're finished. But let's go ahead and do the other ones. Float voltage would also be important. So we'll go ahead and adjust that. I think according to Steve's slides, the table of settings there was recommended 2.25 volts per cell. So again, for 24 volts, that would be 27 volt set point for float. But again, we're going to put the 12 volt nominal value, so the controller will automatically multiply it by 2. So 13.5 volts is what we really want it to be. We'll go ahead and do the same thing there. Rinse and repeat. All right, so far we've done the absorption voltage, the absorption time, the float voltage. Let's see, some other important things you may want to adjust. If we go back one level to the custom screen, the custom menu here, back where you see load control, that's a popular setting to change. We can go ahead and change the LVD. That would just be under the normal category within the load control menu. You see there you can choose from LVD or LVR. That's the low voltage disconnect, and then the low voltage reconnect. So low voltage disconnect, we have it commonly set at 11.5 as sort of the default factory value for many of our controllers. But again, this is custom programmable. In many cases, you know, the LVD set point is highly dependent on your battery capacity and your desired depth of discharge. You know, ideally, you don't want to discharge below 50% for these batteries, as Steve mentioned earlier. 11.5 may be a little bit below that in most cases. You know, maybe 25 to 30%, or sorry, that would be 70 to 75% depth of discharge. So if you want to be a bit more conservative, maybe you just go up to the 12 volt nominal value. So we'll just hold that, program that up to 12 volts there. Save it, set LVD, yes. So that's saved now. And then the one other measurement or custom programming modification we can make is concerning the temperature compensation that Steve also mentioned the importance of. So to access that, we're actually going to go to the advanced menu. I'm sorry, that is still within custom, but we're going to go up one to the advanced menu. Now, it does give you a warning here to try and deter anybody who wants to tamper with the advanced settings. We are aware of that. We want to go ahead and enter. So now we can again go back into the charging metrics here. We should find, if we scroll down, temp comp value that we can edit. So that's the actual temperature compensation factor. As you can see here, it's currently it's set on 0, which again may be useful if you just want to disable temperature compensation altogether, maybe for lithium batteries or something like that. But the factory setting is negative 29 millivolts per degree Celsius, and again that's the 12-volt nominal value. So for 24 volts, it would be minus 60 millivolts per degree Celsius. So we can go ahead and again just put the 12-volt nominal value in there, and it will go ahead and adjust that based on the 24-volt setting. So maybe we'll just set it to minus 30, which is the minus 5 millivolts per degrees Celsius per cell. There we go. We'll save that. Temp comp. All right, that's saved. So now we can go ahead and back out to the main menu, and we'll go one level back here. We're going to go till we see the commands. This is right at the main menu, so it's the first screen you see when you press the down arrow from the rotating status screens. You'll enter the commands menu, and right at the top there, you'll see reset control. You go ahead and push that once. It'll give you a confirmation prompt. Yes, we're aware. Do that really quickly. Power cycles the controller, and you're up and running again. So now tells you the serial number, the hardware and software version, the model number, and so forth. Now you're back in the rotating status displays. But if you go back to the settings, or I'm sorry, the custom menus, you can actually see that the new settings have taken effect now. So the absorption voltage should read 15 volts that we had programmed earlier, and so forth for the other programming modifications we made. So that pretty much gives you a little bit of a walkthrough on the navigating the meter display on the ProStar MPPT. I'll go ahead and go back to the PowerPoint here. And just wanted to mention a couple other nice features of this controller that are available. One of them is for remote monitoring. This would require an optional Ethernet accessory, and then you can communicate over an IP network. You can access the internet. What it's showing here is what's called the live view display, which is configured in this case specifically for the ProStar MPPT. So it will show you sort of the most important metrics, system metrics on the array side, the battery, and the load side. You have some other conditional metrics particular to what's occurring on site, system level, and you can see that through just a nice HTML formatted web display you can navigate to on a local area network or on the internet. And then also to show you here, one of the other screens that's available through that live view interface is the data logging screen. You can see here each controller has a certain amount of internal memory storage for a number of days, logging a fixed number of variables. And for the ProStar MPPT, it's actually capable of logging over 256 days of data. Right here, you just see based on the reference point of today, going back the past 16 days from that reference point. And again, it'll give you the actual day and hour count that the controller has been operational as well. So once the internal memory of 256 days has been has met capacity, it will start to write over the oldest events. So you'll always have the most recent 256 days, or depending on how many variables you're logging, will dictate the capacity of memory storage. So here, just some useful information. Again, have to kind of look through at what's important to you, but I noticed some zeros here in the absorption charging stage here for these days, and you can actually see that that corresponds with a pretty low minimum battery voltage in both cases here, where these zeros are popping up under the absorption. The controller didn't even make it to absorption on those days, and you can see they started off with a really low battery voltage, and that's why. So that could be problematic if it's a pattern. If it becomes a pattern, like Steve said, you want to go through a full absorption at least once a week. But again, you can see here where you have these nice round numbers, 240 minutes. Again, that's 4 hours of absorption. When you have odd numbers that are not complete, you didn't make it all the way through absorption. So you just want to make sure that you're going through a full absorption stage at least once a week, and that you don't have excessive loads that are perhaps draining your battery lower than expected overnight or on cloudy days. So that's just some useful information that's available for viewing or monitoring with some optional accessories on the ProStar MPPT. And that controller certainly comes highly recommended. It's very versatile. Without taking up too much more time, I'll go ahead and throw it back to Steve. Steve, are you ready for me to hand over the controls again?
Yep, I'm ready.
Okay. All right, should have it now.
Okay, everybody hopefully should be seeing it by now. Didn't look like it changed much, but we're going to talk about battery maintenance and how important battery maintenance is. When you're dealing with lead-acid batteries, especially flooded lead-acid batteries, even valve-regulated lead-acid batteries, even though they say they're maintenance-free, they're not really maintenance-free, because how many of us have gone out to a site where we're doing some checkup work or there's a problem on a valve-regulated set of batteries, and you walk up to it, you find that a terminal's burned off one of the batteries. That is part of the maintenance, checking your connections, making sure your connections are solid, especially with you have a lead bus bar or a lead terminal with stainless steel hardware and a copper wire or a copper terminal. All three of those things expand and contract at different rates. So there's always a little bit of maintenance on a battery bank, regardless if it's lead acid, flooded lead acid. Even lithium batteries have maintenance, so there's some slight maintenance issues. Anyway, so battery maintenance and generally for flooded lead acid batteries, every 45 to 90 days, you really should get in the habit of looking at your specific gravities, looking at your rested and loaded voltages, just taking a look at them and see where they're at. And the reason I say that is that when a battery is in the process of failing, or a battery bank's in the process of failing, 99 times out of 100, it doesn't fail overnight. It's going to fail over a 4 or 5, 6, 7 month time period, where if you catch it before it truly fails, and you have that data to bring to the battery manufacturer, they're often going to replace it under warranty without it getting bad enough where it's going to affect the rest of the bank. The problem is where most customers, most installers are at, they don't realize the batteries have got a problem until the lights go out. And when the lights go out, you're probably also caused damage to the rest of the battery bank, which the manufacturer isn't going to cover. So every 45 to 90 days, it's a good idea to get in the habit of measuring, recording loaded your resting and loaded voltages. It's a good idea to check and record your electrolyte levels, your specific gravity measurements. And what I tell people to do, especially if you have a single 1-string or 2 strings of batteries, check the odd number of batteries on odd months and the even number of batteries on even months. You're having your labor to do it. You're having the time you've got to deal with it, but you're getting a full recording at least every couple months. If you have 6 parallel strings of batteries, that kind of defeats the fact. I mean, you got to check 144 cells. It may have been cheaper to buy those small capacity batteries and put in 6, 7, 8 parallel strings of batteries, but the amount of time you're going to be checking cells or replacing batteries because of problems, it's gonna outweigh what you spent on the battery in the first place. Make sure your battery temp sensor is still attached. Make sure it's properly attached. Make sure rats haven't chewed into it. And mice love to chew on these little plastic wires all the time. They love to strip, rats, mice, chipmunks, squirrels. They all love that stuff as bedding. So check the ambient temperature of your battery room and check your battery temp sensor. Make sure everything's all good. Move the batteries around. Check the cell integrity and make sure that the batteries are still in good shape. Make sure they haven't frozen. Batteries can and will freeze, especially in cold temperatures. Check your turbo or your battery connections. Don't just tug test your connections. Put a wrench on them, back it off a half a turn, and retorque them down. If you hear it snap, or if it's stiff to move, that terminal connection was probably already loose, and you've got a problem already developing there. So you've got to take that, replace the hardware, clean that connection probably. Check the battery monitoring equipment, verify the operation. You want to make sure that your monitoring equipment's, giving you the right numbers. And then at the end, top off with distilled water as necessary after a full charge of the batteries. So, while you're doing some of the sub work, turn the chargers on, let the chargers run. Don't check specific gravities or tighten connections when you're doing that. But, when you're wiping the batteries down or something like that, you're not going to cause a spark. Check your connections. Make sure you check your finish that full charge and then work on your connections. Okay, so every 180 days, test your ventilation. It's important to make sure that the ventilation is working. If you have a flooded lead-acid battery bank, you should have some sort of active ventilation that's bringing air out, extracting air from the room, especially during charging. Hydrogen is very corrosive. It'll cause corrosions on terminals. It'll cause corrosion inside inverters. It'll cause relay problems. It'll cause lots of problems, especially if you're not extracting that ventilation from the room. Again, check for high resistive connections. Loosen the terminals, retighten. Again, this you want to do when your system's not charging. And I'll show you a picture. I'll show you what happens after that. Check your cables, make sure they're not broken or frayed. A lot of people use non-UL rated welding cable, and it tends to break down quicker than standard welding cable or UL rated welding cable or battery cable, so be cautious of that. Verify that your charge controllers, your inverters, are outputting the correct voltage. Again, sometimes you can get problems with inverters, sometimes you can get problems with products that you want to detect. Especially those in the northern hemispheres, make sure you check the cells for cracks or evidence of leakage. Batteries do and will freeze, especially if they're run at a low specific gravity over the winter. It gets really cold and it can freeze. And last but not least, make sure your grounds are still there. Some products don't work very well when they're operated in an ungrounded environment. Matter of fact, in some cases you can even electrify the pipes in the house if you're ungrounded. So be cautious with that. Battery maintenance. Something that's important to understand about battery maintenance. This is an actual email I got from a customer. They had some corroded terminals. The husband decided that he was going to clean the terminals, took out his grinder, started grinding on the terminals while the batteries were charging. There are 2 gases that come out of your batteries when you're charging those batteries. Those 2 gases are hydrogen and oxygen. The problem is you get a nice little spark in there, and that you have a good possibility of someone getting hurt. In this particular case, the customer didn't get hurt. But this is another case in Jamaica where the customer was checking his connections while he was charging his batteries. Again, it's Jamaica. It's not a code compliant installation, but it is Jamaica, or not NAC code compliant. But this gentleman was checking his batteries when the batteries are charging. He shorted his spanner from positive to negative. It arced and it blew the top off of these 3 batteries. Unfortunately, the customer had his face over the top of the batteries, and when that happened, the electrolyte from the batteries, which contains 20 or 28% sulfuric acid, sprayed in his face and has blinded him in his right eye. So make sure when you're doing maintenance on your systems that you do have the proper safety equipment. If you don't, you're eventually going to get yourself into trouble. So, battery maintenance. Water is not created equal. You can use distilled water. Do not use bottled drinking water. Do not use rainwater. Do not use water collected from the air conditioner, from the condenser of the air conditioner, and do not use lake or river water. Period. If you do, doesn't matter whose batteries you purchase or you install, you will void the warranty in those batteries. They will eventually find out what you're doing. Okay. You can use deionized water or reverse osmosis water, but you need to test it to make sure that the water is good water. You want 0 to 5 parts per million. You want a pH as close to 7 as possible. Distilled water is usually always pretty good. I've only had one place, and that was Haiti, where I was testing distilled water, and it came back at 15 parts per million. It was a little high, but that's what they're stuck with. Unfortunately, they've got to use that. I was just recently up in Northern Ontario. They were using the cast-off water from distilling of maple syrup, but they weren't cleaning it any further, so the water was testing at 500 to 1400 parts per million, and so that was damaging. It was introducing that, coupled with improper temp sensor mounting and improper charging. The batteries were so poorly corroded, the plates were turning to mush. Here's a picture of what it looks like when you run your batteries dry or when you run excessive heat or corrosion. This picture here, this is the water line. These are the water lines where the batteries are run dry. You can see the top part of this plate. The top part of the plate, you can see the excess of corrosion on the plate versus the bottom part of the plate. Okay. On this particular plate, you can see a water line right here where it was run dry, and you've got the corrosion on the top. But this is also excessive heat, and that heat is caused by corrosion. I once got a phone conversation from a gentleman in the Bahamas who called me up and complained that his batteries were getting over 65 degrees Celsius when he was charging them. I asked him what his specific gravity was, and he told me he couldn't measure specific gravity because his water level was too low. You got to have the plates covered in water. If they're not covered in water, they start to oxidize, they start to corrode, and that will cause failure. When you're filling your batteries, most all renewable battery companies nowadays, they have this vent well that's inside the batteries. They want the water level 6 to 13 millimeters below the bottom of that vent well. Okay, if the water level is up here, then what will happen is as the batteries are charging, what will happen is that will bubble out. You'll start losing specific gravity. You'll start losing capacity, and your batteries will last 2 to 3, 4 years, and they will fail. Be cautious of that. Do not overfill. You want to make sure you don't want to underfill. You don't want to overfill. You want to be within that 1/4 inch to a 1/2 inch from the bottom of the fill tube. This is what happens when you overfill. Typically, you see lots of corrosion on the batteries. This is caused by overfilling the batteries. This is caused by putting too much water in the batteries. It overfills, and it aids and abets in getting this corrosion on the batteries. So you want to try to avoid that. All right, so I'm going to change this back over to Jake, and he's going to go through a summary.
All righty.
Oh, you're one slide ahead.
Yeah, sorry, hang on one second. Got too many screens going on here. Okay.
There you go, man.
All right. So just to wrap things up, sort of on both sides here, Steve, thank you very much. It was very comprehensive, a lot of information that I hope will benefit the audience profoundly. Important to consider both sides of the equation here. You got a lot of good, do's and don'ts about, best practices for sizing these systems, batteries in accordance with not only your to offset your load requirements, but also to ensure that the battery is getting properly charged, going through the appropriate stages required for regulation, and of course how to make sure that you have the complementary equipment to provide that functionality on the charging side. And it's really variable. There's not a one-size-fits-all solution that you can say works in any case, for any type of load requirements in any location for any system size. So you really want to pay attention to the sizing process and make sure you're very thorough. And, as far as programming the charge settings with the controllers, always do the custom settings if and whenever possible, to make the assumption that the standard presets provided by the charge controller manufacturer are suitable for your system is not necessarily the case. And so it's always recommended that you please consider custom adjustments. You can do so very easily, again, with a lot of the newer controllers. You have these integrated meter displays that make it very easy to do out in the field. And again, there can be a big difference between doing this and not doing that. So, taking the extra time to make sure you've dialed in the settings appropriately can result in years of difference to your battery lifespan. And of course, having the proper maintenance as well. That's the first and foremost investment that you're trying to protect are the batteries. Certainly the charge controller does its part to treat them appropriately, but again, it's only as good as the settings that are programmed into it, and then it will follow those to a T. So make sure you work closely with your manufacturing partners, your distribution partners, in the case that they are assisting you with the system design. They're able to bring in both sides of expertise to help you design a proper system, for healthy and a long lifespan. So I think that just wraps things up for us. We'll go ahead and take a look at the Q&A. Again, I think, Steve, probably a lot of these questions pertain more to the battery side, but let me go ahead and take a look through. For some reason, I can't see the question dashboard. Not sure why did that go away. Steve, you passed back controls to me, so I should have that. I just have to find out where the question bar. Oh, here it is. Okay. Sorry, I had tidied it away there. All right, let me take a look at what came in. One question from Richard early in the presentation. This past winter, I guess, was quite severe. Took a toll on a couple of cells in 2 of his 6-volt batteries. He's looking for any potential suggestions as far as how to restore them. Steve, do you have any suggestions? Are they salvageable?
It depends, and so I hate to be ambiguous on that answer, but typically you never ever want to charge a battery that is frozen solid. If you do, you have a really good chance of causing bodily injury and harm to yourself, your others, and your home. You want to be really careful about charging a battery that's even gotten mushy, kind of like Slurpee level inside of a battery. You want to make sure that you completely thaw it out 100%. You start charging at like 2.2 to 2.3 volts per cell, and you have to watch it constantly until you're satisfied that the current's not going to run away on you, or the battery won't arc and spark and cause a hydrogen explosion. If the cells just run off, like you get some good cells that are good, some cells that are good, and some cells that are bad. What I would do first is check and make sure your voltage and settings times are correct, voltage and absorption times are correct. If they are correct, then maybe extend your add half hour to an hour to your absorption time and force the controller to stay in absorption. And then the last but not least thing I would do is I would do what I call hard cycling. And what that is you are basically, what you're doing is you're charging the batteries up until they're about 90 to 95% state of charge, and then you load the batteries for a half hour to an hour, and then you charge the batteries, and you load the batteries, and you repeat that process about a dozen times. And a lot of times that'll do better than equalizing a battery. Equalizing batteries is probably one of the worst things you can do, because basically what you're doing is that instead of running 3 miles yesterday, instead of running yesterday, I decided to pass on running. Now today I'm going to run 6 miles because I missed 3 miles I missed on Tuesday. And so all you're doing is if you do that to your body, you have a good chance of physically injuring yourself. That's what you're doing when you're equalizing a battery. Battery companies would rather you charge the batteries in the first place than have to equalize them. Probably too much answer, but hopefully that helped.
I think that's very good. Let's see. One other question for you, Steve. I think you mentioned earlier factoring in some of the losses in the sizing calculations. When you talked about maybe the calculations of absorption time, or the nominal charge current, derated from the peak current. What type of losses were you accounting for there? Is that, losses in the wiring and the connections, or are you talking about other, battery specific losses in the conversion, the energy density and so forth? Heat loss there. I mean, can you elaborate on any of those?
The losses in general, I would say all. And so, like, for example, let's say I've got a 48 volt controller that'll do, say, 60 amps of current. If I'm getting 1,000 watts of solar, 1,000 watts per meter squared on a solar panel, say the solar array is a 3,000 watt solar array, and I'm getting maximum sun value, and my panels are at 25 degrees Celsius, that's going to do roughly that it's going to do that 3,000 watts. Now, realistically, in most places, if the panels are within that 25 to 30 degree window of the sun, you're going to start seeing that solar production fall off. And so you want to be really careful. You may have sized and sold the customer a 3,000 watt solar array, but a 3,000 watt solar array is really only going to operate between 2,000 and 2,600 watts, on average, because you're going to have cloud conditions, you're going to have rainy conditions, you're going to have soiling on the panel. It may not be the perfect angle. You may not be in the perfect angle. I mean, there's going to be a few hours of the day where you will see that, but the majority of the time, that panel spending, that 3,000 watt array is going to be between that 2,000 and 2,500, 2,600 watts. And that's why I derate that, because that's what happens in the real world. You put on a 2 kilowatt array, you're looking probably 15 to 1,800 watts on average of what it's actually going to produce. And that's if you've sized it properly to the charge controller. I can't tell you how many people I've seen that'll put on a 9,000 watt array on two 60 amp charge controllers. And so 9,000 watt array is 180, 200 amps of possible current, but you're self-limiting because now you don't have that third charge controller or even that fourth charge controller to maximize your production while you have production. So you want to be careful with that.
Right. Yeah, those are good points. Let's see here. A little bit of different topic here. For a battery backup system, not normally discharging, I guess just sitting in float, how is that affected with the AGM batteries? I guess this gentleman in particular is using a Magnum inverter charger, basically just trickle charging the batteries continuously. Do AGM batteries tolerate that type of cycle activity or lack thereof well?
Yeah, maybe I didn't get that. I'm thinking back. I probably didn't do a very good job explaining that. Calcium batteries want to float. So calcium batteries, if the battery is connected to grid and it's trickle charging the batteries and holding the batteries there for a long, 12, 24, 36, 48 months, a calcium battery is going to enjoy that more than a lead antimony battery, say a flooded lead acid lead antimony battery. So that would be a better choice. You could use the antimony battery if your client about once every 30 to 60 days shuts off the grid and runs the batteries for a couple hours and then reconnects the grid to go back into charge. Yeah, calcium battery is going to like that backup application. Originally, calcium batteries were used in telecom applications where they sat and float 365 or 360 days a year, and they were only discharged 4 or 5 days a year because of power outages.
Right. Okay. And let's see, what is, maybe this one is hard to answer, but what's the best depth of discharge to maintain, I guess, in terms of optimizing the longevity of the battery bank? I mean, I think maybe it's more widely agreed not to, in typical lead acid installations, it's recommended not to exceed 50% depth of discharge, but is it correct that, even in shallower permutations of that, 20 to 30%, you're going to see an according increase in the longevity of the bank as well?
Yeah. Personally, the way I size my systems, especially those who are full-time off-gridders, and they expect the batteries to last, you're putting in a, like, for example, we're saying to put in a 1400 cycle life battery at 50% depth of discharge. If I can maintain 20% depth of discharges in that battery bank, where I'm only taking it to 80 to 75 to 80% state of charge every single day, but I've got enough solar to keep the batteries, to bring the batteries back to a full charge every single day, that battery ballpark's going to last about 7 to 10 years. If I'm doing a full 50% cycle every single day, that battery bank's going to last you, that 1400 cycles is going to last you about 4 to 4.5 years at the most. So the shallower the cycle and the higher you can keep the average state of charge, the longer that battery's going to last.
Okay. Yeah, that's a big difference. Okay, let's see. Just taking a look through the additional questions here. There's probably more than we can answer. There was one here from Saul. Kind of an interesting question. Why is a charge controller sometimes called a regulator? Is there a difference in the technology or just different terminology for the same equipment? Yeah, it's funny how certain parts of the world. I know a lot of times when I go down to Australia, they'll call them regulators, and sometimes like the AC battery chargers tend to get more of the regulator nomenclature versus the charge controllers, which are seen as specifically DC converters. But yeah, they're the same equipment more or less. It's just difference in terminology depending on where you go. Both their first and primary job is to regulate the stages of charging for the battery to keep them at as high a state of charge as possible without, of course, overcharging. Let's see here.
So I actually got an email. I got a question emailed to me, if you don't mind me. It's actually a pretty good question because it's a tough one. I'm not sure if he's still on because I just sent him a message asking if he's still on. But customer from Greece emailed me and he asked me. Actually, he's still on, which is good. About mini grid or AC coupling systems. the charging settings on AC coupling systems are a bit different than a straight off grid or a grid backup system. The easy, simple answer is that the settings are somewhere in between. And the hardest part about setting up an AC coupling system is you're trying to walk the line, a delicate line of how much power to the sell to the utility versus how much power to the sell to the loads. If it's a utility sellback system, or if it's a straight off grid system that's straight AC coupled, you're trying to walk the line between how much power you're going to use versus how much power you're trying to store. And so with those type of systems, because everybody's using that system differently, the settings are slightly different than what you would do if you were straight off grid or if you were straight grid tie. And so you've got to experiment with it. And I'll be honest with you, I've worked with several Rolls customers on AC coupled systems with various products out there. And it's really a 3 to 6 month discovery process where you're experimenting with certain settings. You start with a setting and you document that setting. You make slight changes, and then you look at the specific gravities when you do your full charge once a week or once every couple of weeks, and you look at those settings. And so the customer has to manage that, regardless of who the AC coupling system is you still have to actively manage that. And that's one of the ugly things that with AC coupled systems is they are, even with some of the supposed smart product out there, you still have to actively manage it. If you don't, eventually what happens is the batteries crash. So just make sure whatever battery company you're working with, you work with the battery company and you work with the company that you're dealing with for inverters and the controllers to adjust those settings to tweak them for your specific uses.
Okay, good recommendation. All right, just to take a little bit of pressure off Steve here. To the charge controller side, the question from, let's see here. Yes, is there a Morningstar controller that works at 36 volt battery output at 20 or to 30 amps? Yes, there is. The 36 volts, sort of an odd nominal voltage, but certainly our charge controllers are capable of being custom programmed to support that. You would have to use a controller that is actually capable of 48 volt charging. And then what you would do is, instead of using 12 volt nominal values, you would essentially put in the equivalent, if you want to call it a 9 volt nominal value. So you would just basically multiply the 12 volt nominal value by 3/4, and then that would be the setting that you would input into the custom programming. So then the controller knows to multiply the 9 volt nominal value by 4 on the 48 volt setting, and you would then end up with an equivalent 36 volt battery output. And of course, 20 to 30 amps. So for the 48 volt output range, you'd have to be in the TriStar or TriStar MPPT category. You can, with the TriStar MPPT, it's available in 30, 45, and 60 amps of output. So even if you wanted to limit it to 20 amps, you can do that through custom programming as well. You can set the max charge limit to 20 amps so that it doesn't go the whole capacity of the controller's output rating. So yeah, either the TriStar or TriStar MPPT would be the recommended charge controller for that particular use. Steve, how you doing on time? I want to make sure I'm not taking up too much of your time.
I'm doing fine as long as people are still here, so it's all good. All I got to do is head to the gym afterwards. So.
All right. Let me just see. I know there's a lot of good questions in here. Some of them are more deep in regards to the system sizing. So we may want to follow up with those outside of the webinar format, but we could do that by email. Steve, this question, again, is sort of open-ended from Bill here, but how does he calculate the effect of battery life without a battery temperature sensor installed? Um, I know you and I talked about it briefly, and again, there's probably some variability to it, but can you perhaps paint a picture of some different case scenarios where you could see a big change in battery life expectancy with or without a temp sensor?
Well, the easy question or the easy answer for that, for as a, I guess you could say, as someone who works for a battery manufacturer and understands their warranty policy, and they're pretty much all across the board. If you don't use a battery temp sensor and it's not correctly mounted, the battery company is going to void your warranty. It's that important to make sure you have a battery temp sensor installed. And the reason for that is if you don't, you are never properly charging your batteries. If you're never properly charging your batteries, why would the battery manufacturer cover it under warranty? It's just like if you buy a brand new car, drive it off the lot, and decide to never change the oil. A year and a half, 2 years, 3 years down the road, the engine seizes up because it's just sludge. They're not going to cover that under warranty either. It's the same thing. So,
Right.
it's hard to tell. There really isn't a calculation to tell how fast it's going to take for a battery to fill. It's not being used with the temp sensor. It depends on where you're at, or where you're at and how heavily the customer's using it. If you're in Hawaii and it's a weekender type house where the client's in the house, for 2 weekends a month, it's probably going to be a negligible issue. But if they're in Hawaii and it's a full-time house and they're cycling those batteries 25, 30% every single day, you're going to see a pretty large effect on the lifestyle of the batteries. I've seen batteries without temp sensors fail from anywhere from, the shortest I've seen is we had one in Hawaii that failed in 12 months because the customer didn't have a temp sensor installed. They had too low settings to start with, and the batteries were never fully charged. And so the capacity of the batteries died, went from 100% to 50% in less than 12 months of use.
Mm-hmm. Yeah, I mean, that says a lot right there. I mean, I guess to kind of piggyback off of that too. I mean, if you were using more, I don't know, maybe aggressive custom settings to ensure that if you were using, say, flooded batteries where, again, they're a little bit more tolerant to overcharging, I guess you would want to, if you didn't have a temperature sensor, which, again, you should have in the first place, regardless, your custom settings would have to be, you'd want to overshoot the manufacturer's recommendation, again, even to err on the side of caution there, because more damage, I think, is seen from the lack of temperature compensation when it comes to undercharging. Is that correct, Steve? Is that the damage
it goes both ways.
Caused there is more both ways?
It goes both ways. If you're undercharging, you're starting sulfation. The longer that sulfation's on the battery, on the plates, the once that hardens, it's hard to get that off. If you're causing too much temperature, if you're overcharging, you're going to see great capacity numbers, but the battery's going to be end of life sooner because you're using that capacity up.
Okay, right.
I mean,
good point. Okay. Yeah, that makes sense. So in either case, again, it's really important to have that temperature sensor so that you're getting accurate. You're not undershooting or overshooting the battery manufacturer's set point recommendations, because in the long term, it can certainly result in deteriorated lifespan. Let me see here if there are some other good questions to highlight for everybody else here. Most here. All right, bear with me a second. Long list of questions. Steve, do you have specific resources for like the equivalent depth of discharge uh, relevant to different voltages of batteries of a certain capacity, specific models within Roll's product range?
We get that request
like
a
an
lot.
equivalent chart where
There, other battery manufacturers do publish charts like that, but without knowing the load that you're running, those charts are false. And so you want to be really careful of that. I can tell you for 100% certainty, your battery, when it measures 2.13 volts per cell with no load for 2 to 3 hours, it's at 100% stated charge. Okay? I can tell you with 100% certainty, when your battery measures 2 volts per cell with 2 to 3 hours of rest with no load, it's at 50% depth of discharge. And I can tell you that if they're at 1.75 volts per cell with no load and that same 2.3 hours of rest, they're at 100% depth of discharge. What I can't tell you is that if your 24 volt battery bank measures 24.6 volts with 8 amps of load, I can't really tell you where the state of charge is because I don't really know the health of the battery bank. And so, because 8 amps of load is different than 16 or 20 amps of load. So you don't really know how much load's on. And the load needs to be, because what's going on inside the battery is a chemical reaction, the load needs to be 100% off the battery for 2 to 3 hours for the battery to stabilize. And in a traditional off-grid installation or a traditional battery-based installation, people aren't going to separate the loads from the batteries to give it them rest. So there's a little bit of conjecture. There's a little bit of, every system is different. You've got to set that for yourself. So a lot of battery companies have caved and they've provided charts like that. But we had a chart like that at one point, and I had to pull it offline because we had people that would call us and email us and be argumentative of us on that chart, even though we had a highlighter saying this is for reference only, and so there was just too many issues that are caused for that. You just, without knowing exactly how much load, without being able to take the Puchert's calculations in effect and the current status of the batteries, it's virtually impossible to tell what the state of charge is based on voltage only.
Yeah, that's a good point, Steve. Thanks for pointing that out. I think, maybe that is good. We got through a fair amount of questions. I know there's several more that we didn't hit on, but perhaps it's best for us to follow up with those offline. Didn't want to take up too much of people's time today. I understand, I know we went quite a bit over the hour, but I hope it was informative for everyone. Steve, I really appreciate you coming on and joint hosting this webinar with us. If anybody has any questions, you should be able to see our contact information up on, let me just see if it's, 1 second. Yep, you should be able to see it there. Our contact information for both me and Steve. Again, you have our email addresses there. If you need to contact us, feel free to do so directly. Appreciate everybody taking the time out. And again, look forward to seeing everybody next time. Steve, any last words?
Again, I want to thank Morningstar. You guys actually organized this and did a great job. So I appreciate being able to work with you guys, and it was entertaining. And I want to thank everybody for attending. So like we had over 200 and some odd people here. So it was a good group.
Yeah, very good. And hopefully we'll do it again soon. Appreciate it, everybody. We'll see you again next time.